Welcome back, psychology research and design students. Today, we're going to be adding ANOVA statistic to your bag of tricks. Okay, so it's really ANOVA, not an ANOVA, but if it helps you to remember that we've got another thing going on, that might help you remember the purpose of this test. An ANOVA, or analysis of variance, looks at differences between groups in the same way that a t-test does. But a t-test is for two groups, and ANOVA has another group, at least 3 groups. We could have 4 or 5 or 10 or 27, although that would be getting pretty excessive when the groups get that large. But the essence of an ANOVA is the same as a t-test. We're looking for differences in the means between this group and this group and this group. We can do an ANOVA between, where the individuals in each group are separate and distinct individuals, or we can do an ANOVA within, where each person gets the different levels of the independent variable, or we can do complex designs that have elements of between and within. People get different conditions in a different order. So we will start with a one-way between subjects ANOVA, where we are assuming we have a nominal or ordinal independent variable, and we have an interval, approximately interval, or ratio dependent variable. ANOVA also assumes, in addition to the independence between people, if we're doing a between subjects, that the data for each group are approximately normally distributed and homogeneous, and we will look to see whether they have varied across the different groups. Random sampling and assignment is also assumed, although sometimes we have to violate this test if we can't get a truly random sample. We may need to go with a convenience sample. So we'd be skeptical about any outcomes that didn't have true random assignment or selection for the study, but we can at least within the design randomly put those people in the groups and make that random assignment part of what we do well in our design. So in a one-way between subjects ANOVA, again, we're comparing the means and the variation among the group here to the mean with the variation here and the mean here and over here if we have a fourth group and so forth. So we will run the test to see if there is more difference between the groups than there is within the groups. This is talking about the between subjects and within subjects variability. How do we do this in SPSS, Dr. Wickline? I'm so glad you asked. How we get started is we go to Analyze, and we want to compare means with a one-way ANOVA. There's actually 2 ways to do it in SPSS, and the second way gives you more complete information, so I'll show you both. For a one-way ANOVA, we want to put our independent variable as the factor here, and our dependent variable as the factor here. In this case, I'm going to look at class standing to see if there is a difference between people in different years in college, freshman, sophomore, junior, senior, on their age. And you might already kind of look and go, yeah, I'd expect those seniors to be older than freshmen, right? So we're starting with a kind of common sense example to help you see what the test really does. Under contrasts, we don't need to do anything. If you wanted to do in your design, instead of testing every group from every other group, you could compare certain sections. That's where we might use contrast. But as we're just getting started, we don't need to do this today. We want to go under options to ask it for the descriptive statistics and a means plot. This is going to give us a line graph that shows us the difference in the means, if there is one, between the different groups. And continue. And then we might need a Posthoc test. What's interesting about ANOVA is it's a distribution that is always skewed and always one-tailed. So even if you're pretty sure you know those seniors will be different from freshmen, an overall ANOVA can't tell you that. All it can tell you is there's a difference somewhere in here. You will need a post-hoc or after the fact test to tell where the difference is, where the variation lies. So we might have these 4 groups we're looking at, and we don't know if these 2 are significantly different, these 2, these 2, these 2. And that's what that post hoc analysis does for us. It takes each pair within the broader group to figure out how that set or pair is different. So there are different kinds of post hoc tests we can run. One kind is called LSD, or least significant differences. This is the least restrictive and most flexible kind of post-hoc test we can do. So it's kind of interesting that it's called LSD, no? Another kind that we can do is called the Scheffé test. Mathematically, the Scheffé test is a little bit more picky or restrictive on how different things have to be before we call it significant. Some textbooks, including the one we're currently using in class, prefer the LSD method to be more flexible. Other textbooks and statisticians like a little bit more rigor, and they will recommend Scheffé. So I'm going to show you both so you can see a little bit of how the differences are in these two kinds of post-hoc tests. A third kind that is frequently taught to beginning students is the Tukey test. And Tukey is nice, but it's a little bit touchy. You have to have exactly the same number of people in each of the groups to use the Tukey test efficiently. So while it's really nice if you've got a great controlled experimental design that has exactly the same number of people in each group, this doesn't often work when we're doing quasi-experimental studies or real-life studies where the sample sizes are uneven. So we will stick to primarily LSD and Scheffé for a post-hoc, after-the-fact test to see where the group differences are. We will set our basic significance level at 0.05. This is our alpha level, our preset value that tells us how different each of the pairs has to be for us to consider it significant. And we will learn later this semester about ways or reasons we might make this a little more restrictive, pick a slightly smaller alpha level to reduce our risk of type 1 error. But for now, 0.05 will do. Click Continue. And now that we've looked at our post-hoc tests and options, we can click OK. And first what it'll do is show us our descriptive statistics, how many people in each group, the mean for each group, and the standard deviation for each group, plus standard error, confidence intervals, which is estimates of variability, and our minimum and maximum scores. We will need to report at a minimum the sample size, mean, and standard deviation for each group as part of our test. Then we run the ANOVA test, which looks at the variability between groups. Is this group different from that group is different from that group? And also gives us an estimate of the variation within groups. How much do the different people here and here and here vary from each other? When we compare those, we have two parts to our degrees of freedom. Overall, the degrees of freedom is equal to the sample size minus 1. But in an ANOVA, we split that into two parts. We need to know the variation between groups, which is equal to the number of groups minus 1, and then the differences within the groups, which is equal to the total sample size minus the number of groups. So for here, we had 4 groups, first year, sophomore, junior, senior, so n minus 1 equals 3. We had, if we subtract our total sample size, 256, minus those 4 groups, we get the within groups variability, 252. Together, those will add to our total degrees of freedom, which is equal to n minus 1. Once we know the variability across groups, the F statistic gives us an estimate of whether there is variation in here somewhere that is different for between groups, in addition to what we have within groups. In this case, our F value, sometimes called the omnibus or overall F for the ANOVA test, is significant, which means we reject our null hypothesis that differences don't exist, and we accept our alternative hypothesis. There's something going on here. There is a difference across these groups. Next, our graph will help us see that. As we might have expected, it looks like there is difference across class here. But we still need to figure out which difference pairs are significant. Are these two different? Are these two different? Are these two different? These two, or maybe all of them. Sometimes one pair is significant and none of the other ones are. Sometimes each pair is significantly different. Each group is different from the other group. And again, this is what the post-hoc test helps us to see. If we look at the two post-hoc tests, it gives us the result of the Scheffé test first, where it compares each group, starting with first years, to every other group, sophomores, juniors, and seniors. In this case, each pair is like an independent samples t-test and tells us, is this group different from that one? and we look at our significance level to tell if it's meaningful. In this case, first years and sophomores did not significantly differ. These two groups were about the same age. However, our first years were different from the juniors, that's significant, and from the seniors, that's significant. Then we go on down the list. Are sophomores different from first years? We looked at that already. Are sophomores different from juniors? Yes. Are sophomores different than seniors? Yes. Are juniors different than seniors? No. So what we have is a way to kind of summarize which groups are different from each other. This can take a little bit of explanation the more groups you have in your design to do in your results, because you've got to tell whether each pair was significantly different from each other pair. In this particular case, first years and sophomores did not differ from each other. Juniors and seniors did not differ from each other, but the rest of the groups were different in each pair. So first years were different than juniors, first years were different than seniors, sophomores were different than juniors, sophomores were different than seniors, juniors were not different than seniors. Realize then, when you've got 4 groups in an ANOVA, this can get a little complicated, and sometimes it's up to you as the researcher to decide how to explain this overall pattern. What might be happening here, because this still looks pretty different from everything else, right? Each group seems to be different. It might be something going on about sample size, right? These 2 groups didn't differ a whole lot, and these 2 groups didn't differ a whole lot. But our sample size is pretty uneven. We didn't have a lot of first years. We didn't have a lot of seniors. And so we might explain that the pattern is along what we'd expect, but that sample size might be having an effect. Actually, for ANOVA to work really well, we need at least 20 people in each of our conditions. If we have less than 20, we get a little bit suspicious about making comparisons with that group and the other groups. We might still do it, but we have to realize we may not have the most reliable or generalizable results. So, to recap, if you're reporting a between subjects ANOVA, we need the descriptives here. We need the inferential results here with the degrees of freedom, F, and significance level. And we also ought to talk about the post-hoc tests. And lastly, the effect size. Effect size, you might remember, is a difference between the means that is not affected by sample size. So it's a measure of the size of the difference, not the probability. The trick is that the first way we ran the test does not show us effect size, and we could calculate it by hand. Or we can go to Analyze, and the second option, General Linear Model, and do a univariate, which is a 1 outcome, ANOVA. Put our dependent variable in the first box, our independent variable here, dependent and independent. We go to post hoc and ask for our same post hoc tests, LSD and Chaffee, but we can ask it to compare our marginal means. So we would put overall and our variable here to display the means to compare the effects with an LSD comparison, that's the least significant difference. And if we go to options, we can get descriptives, effect size, power, right? And this will help us be able to see that effect size without calculating it by hand. And lastly, under plots, we can ask it to do a plot for our variable either as a line or bar chart and show us the error bars or some of the difference within the variation within the groups in addition to between. So you will, if you run this analysis, it'll still give you the mean standard deviations in N. It'll still give you the degrees of freedom between, within, the error to get your omnibus omnibus F value and probability here. But it also gives us a measure of effect size here, our partial eta squared. So this is a small effect. And here is our comparisons for post hoc tests. Chaffee, again, post hoc, And when we run that plot, it not only shows us the mean difference,